We have discussed in very detail the concept of four vectors in the previous lecture. And after getting the idea of four vectors, today we will see some important examples of four vectors. And in this regard, first of all, we are going to know about the velocity 4 vector. You can say this velocity 4 vector is also called 4 velocity. Okay. As you have learned that any 4 vector has 4 components in 4-dimensional Minkowski space, and so any 4 vector is expressed just as the in terms of the components of the vector. So this velocity 4 vector is denoted by the symbol u mu. Okay. And if you consider that the 4 components of this 4 velocity vector are u1, u2, u3 and u4, then we simply define this velocity 4 vector like this: u mu equal to u1, u2, u3, u4, as you can see this equation 1. Now our aim is to find what will be the values of these components u1, u2, u3 and u4 of this 4 velocity. Okay. So starting from the definition of velocity or component of velocity, you can find the expression for these components. As you know, if you want to find the value of u1, that is the first component of 4 velocity vector, then this is defined as dx1 by d tau. Here you can see I have written tau. Actually this tau is proper time. What is this tau? Tau is called proper time. Proper time. You have learnt about the proper time and the dilated time in the previous lectures when we have discussed in very detail the time dilation formula in special relativity. And you know, according to that time dilation formula, the dilated time t is equal to tau over 1 minus u square over c square's square root. Okay. So in fact, this dx1 by d tau, which is equal to u1, can be written as dx1 by dt times dt by d tau. Okay. Because you can see that this t is just a function of tau. Okay. Now, as x1 represents the x coordinate, so instead of x1, you also may write this as dx by dt, and this is dt by d tau. Now, from time dilation formula, you know t is equal to tau over square root of 1 minus u square by c square. So if you will take differential, then you will see that dt will be simply equal to d tau over square root of 1 minus u square by c square. And therefore you can see this dt by d tau will be simply equal to 1 over square root of 1 minus u square by c square. So for this factor dt by d tau, we can write 1 over root over 1 minus u square by c square. And this dx by dt, you know, this is actually the x component of velocity, and this is denoted by the symbol ux. So simply you can say that the first component of velocity 4 vector can be expressed as u1 equal to ux over square root of 1 minus u square by c square. In fact, in the similar manner, you can also find u2, u3 and u4. You have only changed these subscripts. Instead of 1, when you will write 2, then here there will be uy. When you will write u3, then there will be uz. Okay. But I have actually calculated these components also in the same manner. You can see here u2, you will define it dx2 by d tau, and this can be written as dx2 by dt times dt by d tau. You have seen that this dt by d tau is equal to 1 over root over 1 minus u square by c square. And x2 means y, so dx2 by dt is written here dy by dt. And you know this dy by dt is equal to uy, and dt by dt you have just seen this is 1 over root over 1 minus u square by c square. So you can say that u2 is equal to uy divided by root over 1 minus u square by c square. Okay. In the similar manner, we will define u3. This is dx3 by dt, and this will be written as dx3 by dt times dt by dt, and x3 is written for z, so this is dz by dt times dt by dt. Again, dz by dt is uz, and dt by dt is equal to 1 over root over 1 minus u square by c square. So in this way, you can see that these u1, u2, u3 can be calculated by this idea. Okay. So I will suggest you, when you find the expression for u1, you can also write these two relations for u2 and u3 directly, simply changing the subscripts. Okay. Now we will find the fourth component of this velocity 4 vector, which is denoted by the symbol u4. In the similar manner, you can define it. This is dx4 by dt, and this will be written as dx4 dt times dt by dt. Now you know that this x4, which is fourth component of the position 4 vector, this is actually equal to ICT. So instead of x4, I have written here ICT, and you also know that this dt by dt is equal to 1 over root over 1 minus u square by c square. Now IC is constant and dt will be 1. So this derivative will be simply IC. So this u4 is equal to IC over square root of 1 minus u square by c square. So you can see in this way we have obtained all the four components of this velocity 4 vector. Now let us substitute all these values in this equation 1, where we have defined this mu, which is velocity 4 vector. Instead of u1, u2, u3 and u4, you can substitute these values. So you can see u mu will be equal to, instead of u1, we will write ux by root over 1 minus u square by c square. And instead of u2, we write uy divided by root over 1 minus u square by c square. And instead of u3, we write uz over root over 1 minus u square by c square. And at the place of u4, you can see this is the expression for u4. This is IC over root over 1 minus u square by c square. Now you know that this ux, uy and uz, these are actually the three components of a three-dimensional velocity vector in 3D space or Euclidean space. So, and this velocity vector u, you know, this is in fact uxi plus uyj and plus uzk. So instead of this ux, ui, uz, we can coin these three expressions just in one expression, and we write u mu equal to vector u, this is three-dimensional velocity vector, divided by root over 1 minus u square by c square, and the fourth component is addition. Okay. So as I have told you earlier in the previous lecture, that any 4 vector, let us say there is a 4 vector a mu, then we simply write a mu equal to vector a, which is the three-dimensional vector in 3D space, and IAT. Okay, IAT. So you can see in here this vector a is represented by u over root over 1 minus u square by c square, and at is c over root over 1 minus u square by c square, and at the place of I there is I. Okay. So in this way we have obtained all the 4 components of a velocity 4 vector. Now we will see what will be the magnitude of the square of the velocity 4 vector. You know that magnitude of a square of a 4 vector is defined is expressed like this. This is u mu times u mu. And you know, you have learnt in the previous lecture that the square of modulus of a 4 vector is simply equal to sum of the square of the 4 components of that vector. Okay. So this u mu times u mu will be equal to u1 square plus u2 square plus u3 square plus u4 square. And if you write u4 equal to I times ut, then you know this u4 square will be I square ut square. But I square is minus 1. So this expression can also be written like this. This is u1 square plus u2 square plus u3 square minus u2 ut square. Okay. Now let us substitute the values of these u1, u2, u3 and ut. Okay. You can see u1 is ux over root over 1 minus u square by c square. So when you will square it, this will be simply ux square over 1 minus u square by c square. And u2 square will be uy square by 1 minus u square by c square. And u3 square is uz square by 1 minus u square by c square. And ut square, this is c by root over 1 minus u square by c square. So this will be c square by 1 minus u square by c square. Okay. Now, if we will add the first 3 terms, see here, as the denominator is same, so the LCM will be simply 1 minus u square by c square, and this will be ux square plus uy square plus uz square, and minus c square over this much, this term remains at each. Okay. Now you know that this ux square plus uy square plus uz square, this will be simply equal to u square. This is actually the component of 3-dimensional velocity vector, and the sum of the square of these 3 components give the resultant velocity vectors square. So this is u square by 1 minus u square by c square minus c square by 1 minus u square by c square. Now let us take the LCM and simplify this result. You can see this will be simply u square minus c square over 1 minus u square by c square. See here, I have taken the LCM and the result is u mu times u mu equal to u square minus c square over 1 minus u square by c square. Okay. Now when you will take the LCM, this c square, this will be c square minus u square divided by c square. So that c square in multiplication will be in the numerator. Okay. Now take minus 1 or simply minus as a common factor. Then this will be c square minus u square, you can see here, and divided by c square minus u square times c square. Now this will cancel out and your result is what? This is u mu times u mu equal to minus c square. This is a very important result. You will find that in several university examinations or different competitive examinations where objective questions are asked, this question is invariably asked. There will be 4 options you will given, and you have to select the correct answer for the square of the modulus of 4 velocity vector, and the option minus c square will be correct. Okay. Now as you know that this c is a universal constant, its value in all reference frame is same. So if we will find the square of the modulus of the 4 velocity vector in S prime frame, then that will be written as u mu prime times u mu prime, and thus u mu prime times u mu prime will be also equal to minus c square, because you know that this c is a relativistic invariant. Okay. So we can say that this product will be simply equal to u mu times u mu. So we simply say that the square of the four velocity vector is a Lorentz invariant, or you can also say that under Lorentz transformation this will remain invariant. Okay. Now, as I have told you in the previous lecture, that some of the authors also define the modulus of a square of a four vector in this manner. It is defined as ut square minus u1 square minus u2 square minus u3 square. So this will be simply equal to minus u1 square plus u2 square plus u3 square and minus ut square. But you have seen that this sum is equal to minus c square. So minus minus will become plus, and then we simply say that this product u mu times u mu is equal to c square. So you can write the square of the modulus of four velocity vector is equal to either minus c square or plus c square. This is just a convention. It depends on you that which convention you follow. But generally the people follows this convention which I have mentioned earlier. So normally we say that the product of u mu and u mu, that is the square of the modulus of four velocity vector, is equal to minus c square. But when we will adopt this convention, then we can write that this u mu times u mu is equal to c square. Now, as in theory of relativity, this constant c always comes in our expression. So there is a tradition that we simply take the value of c equal to 1. This is for simplicity. It does not mean that c is actually equal to 1, but there is a convention that we can take the value of this universal constant equal to 1 to simplify the calculation. And so that if you adopt that very convention where c is assumed to be equal to 1, then we simply write this product u mu times u mu equal to 1. Okay. So I have mentioned it here, you can see. So this is all about the four velocity vector. Now we will see the another very important example of the four vector, which is called momentum four vector. This momentum four vector is also known as energy momentum four vector. Okay. Now we will define again the four components of this momentum four vector or energy momentum four vector. If you denote the momentum four vector by the symbol p mu, and you assume that p1, p2, p3 and p4 are the four components of this momentum four vector, then we will simply write p mu equal to p1, p2, p3, p4. Okay. Again, our aim is same. You have to find the values of all these four components. Okay. As you know, this P1, which is the first component of the momentum four vector, this is defined as m naught u1. M naught, you know, this is rest mass of the particle, and u1 is the component of first component of velocity four vector. Okay. Now you have just seen that what is this u1. You can see the result. We have obtained the expression for u1 here, and we will substitute that value in that equation. You can see u1 is equal to this much. This is ux over root over 1 minus u square by c square. So instead of u1 in that expression, we will now write ux over root over 1 minus u square by c square. But you have definitely studied the relativistic mass variation formula in special relativity. In the previous lecture, I have discussed this relativistic mass variation in very detail. And you have seen that actually this m naught over root over 1 minus u square by c square, this is simply equal to m. This is actually the relativistic mass, m. So instead of m over root over 1 minus u square by c square, we write here m. So, and u1, you know, sorry, u1 is equal to ux divided by this one. So this is simply m times ux, and m times ux in case of the three-dimensional space, this represents the x component of the three-dimensional momentum vector. Okay, so p1 is equal to mux, which is equal to px. Now in the similar manner, you can find the value of second component of this momentum 4 vector. This will be defined by m naught u2. Again, you have seen what is u2. u2 is equal to uy divided by root over 1 minus u square by c square. Okay, and again m naught divided by root over 1 minus u square by c square is equal to m. So this is m into uy, and you know m into uy, this is simply the y component of the three-dimensional momentum vector. This is denoted by the symbol py. And in the similar manner, you can define p3, and that will be equal to pz. See here, p3 is defined as m naught u3, and you have seen that u3 is equal to uz divided by root over 1 minus u square by c square. And this will be equal to muz, and this muz is equal to pz. This is actually the z component of the three-dimensional momentum vector. Now, in the similar manner, you can find what will be p4, that is the fourth component of the momentum 4 vector. This will be simply m naught into u4. Okay. Now, you can see the expression for u4 we have obtained just now. You can see here. This is the expression for u4. You can see this is your u4, and u4 is equal to this much, that is ic divided by root over 1 minus u square by c square. So at the place of u4, we will use this very relation, and so it has been written here that instead of u4, this is ic divided by root over 1 minus u square by c square. Okay. Again, m naught by root over 1 minus u square by c square, this is m. So this is imc. Okay. Now you know the very famous mass energy equivalence relation of Einstein, and according to that energy mass equivalence relation, E is equal to mc square. So if you want to express this mass m in terms of energy, what will be this m? M will be simply equal to E over c square. Okay. So instead of m, I have written here E over c square. Okay. Now 1c will cancel out, and this P4 is equal to IE divided by C. Now you can see that we have expressed the fourth component of momentum 4 vector in terms of energy, and that's why this momentum 4 vector is also called energy momentum 4 vector. This is the reason why it is called energy momentum 4 vector, because its fourth component is expressed in terms of energy. Okay. Now you can substitute the value of these P1, P2, P3 and P4 in equation 1, and so P mu, which is the momentum 4 vector, this is equal to Px, Py, Pz and Imc. Imc here you can see, but Imc, you have seen that this is equal to IE divided by C. This is the fourth component. And instead of this Px, Py, Pz, you can write vector P. Actually, this vector P is what? This is mass into velocity vector u in 3D space. Remember, this vector u is velocity vector in 3D space. And this can be expressed as Pxi plus Pyj plus Pzk. Okay, or muxi plus muyj plus muzk. Okay, you can write. So in this way we have obtained the uh, all the four components of this momentum 4 vector. Okay, now again we will find what will be the magnitude of the square of the momentum 4 vector. What will be this? Again we will find. So see, the square of the magnitude of the 4 momentum vector, this is denoted by the symbol p mu times p mu, and you know this will be equal to sum of the square of all the 4 components. So this is p1 square plus p2 square plus p3 square plus p4 square. But you have just seen that P1 is equal to Px, P2 is equal to Py, and P3 is equal to Pz. Okay, and P4 we have obtained that P4 is equal to IE over C. Okay, so when you will square it, this I square will be equal to -1. So the fourth term is minus E square by C square. Okay, now you know that Px, Py, Pz are the x, y and z components of a three-dimensional momentum vector in 3D space. So this sum Px square plus Py square plus Pz square will be equal to P square. This is actually the square of the magnitude of the resultant linear momentum vector in 3D space. So this expression can be written as P square minus E square over C square. Okay. Now let us take the LCM. This will be in fact P square C square minus E square divided by C square. So if you will take minus as a common factor, then this expression will be E square minus P square C square over C square. Now definitely you know, and I have discussed this relation very detail in the previous lecture. You can see the previous lecture on this special relativity. I have discussed the Einstein's mass energy equivalence relation and the energy momentum relation. Actually, the relativistic relation between the energy and momentum, we write E square equal to P square C square plus m naught square C4. This is a well-known formula of special relativity. And you can see my video on this formula for the proof of this formula in this playlist which have dealt very earlier. Okay. So from here you can see this E square minus P square C square will be equal to m naught square C4. So let us put this value of E square minus P square C square here, then our result will be what? P mu times P mu equal to minus m naught square C4 divided by C square. Okay. Now this C square will cancel and here there will be power 2. So this P mu times P mu, this is equal to minus m naught square C square. Okay. Again, when you will actually use the another convention, that is when we say that this square of the magnitude of the 4 vector is written by at square minus a1 square minus a2 square minus a3 square. If you will adopt that convention, then this P mu times P mu will be what? Simply sign will change. Then it will be equal to m naught square C square. Okay. So this is all about the momentum 4 vector. Now finally we will see the third very important example of this 4 vector, and this is actually the acceleration 4 vector. Okay. If you consider that this acceleration 4 vector is denoted by the symbol a mu, and a1, a2, a3 and a4 are its component, then you simply write this equation 1. A mu equal to this much, or equivalently you can write it as a1, a2, a3 IAT. A4 is written as IAT. Okay. Now, again our aim is same. We will find the values of A1, A2, A3 and A4. Actually, when A1 will be calculated, then in the light of that equation, you can easily write the expression for A2 and A3. Although calculation of A4 will be somewhat different, so that will be calculated independently. Now see, you know that acceleration is simply the time derivative of velocity. Acceleration means time derivative of velocity. It means when you will differentiate the velocity with respect to time, then you get acceleration. So the first component A1 of the acceleration 4 vector will be defined by du1 by d tau. Again, you can remember that this tau is the proper time. Okay. And this can be written as du1 by dt times dt by d tau. Okay. Now, just you have seen that this u1 is equal to what? This is ux divided by root over 1 minus u square by c square. So instead of du1 by dt, we write d dt ux by root over 1 minus u square by c square. And just you have seen that this dt by d tau is equal to 1 over root over 1 minus u square by c square. Okay. Now, take this factor which has been written in last. Now, we write here it. This is 1 by 1 minus u square by c square. Now, we will evaluate this derivative d dt operated on ux divided by this much. You can see here there are two functions, or you can say that there is a product of two functions. The first function is ux and the second function is 1 over root over 1 minus u square by c square. So you can apply the formula or the rule for getting the derivative of product of two functions of calculus. So let us operate this operator on ux. So this will be dux by dt, and the second factor 1 over root over 1 minus u square by c square is kept at each. Okay. And plus, now we will take this ux outside of the operator and we will differentiate 1 by root over 1 minus u square by c square. Okay. So this operator d dt has been operated on 1 by root over 1 minus u square by c square. And this has been written like this in 1 minus u square by c square to the power minus half. Okay. Now, in dot symbol, you know that when we differentiate any function with respect to time t, then we represent that derivative in dot symbol. So this dux by dt is simply written as u dot. Okay. And so this is u dot and divided by root over 1 minus u square by c square. Okay. Now ux is at h. Now let us try to differentiate this function 1 minus u square by c square to the power minus half. As you can see, this is just a function of function. So this 1 minus u square by c square whole to the power minus half, first of all, this will be differentiated with respect to 1 minus u square by c square. And what will be that? That will be minus 1 by 2 times 1 minus u square by c square to the power minus half minus 1. Minus half minus 1, that will be minus 3 by 2. Okay. Now, this 1 minus u square by c square will be differentiated with respect to t. As you know, 1 is a constant, so its derivative will be 0. Okay. Now, 1 by c square is constant, it is taken outside. And u square will be differentiated with respect to t. This is again a function of function. So derivative of u square first of all will be with respect to u, and that will be 2u. And then u will be differentiated with respect to t. So this is du by dt. I hope you have understand this differentiation. Okay. Now see here. This 2 and this 2 will cancel out. Okay, and this minus sign and this minus sign will become plus. Okay, and in numerator, what are present? You can see this is u, and the du by dt will be written as u dot. Du by, instead of du dt क्या लिखेंगे हम लोग? U dot, and this is ux. So ux into u dot will be in numerator, and in denominator there will be 1 minus u square by c square to the power 3 by 2 plus 3 by 2. Okay, so you can see this result here. This a1 is equal to 1 over root over 1 minus u square by c square times ux dot over this much. This is the first term, and the second term is ux times u into u dot, just you have seen, divided by c square times 1 minus u square by c square to the power 3 by 2. Okay, so in this way you have obtained a1, but our aim is again to change this quantity u times u dot. What is this u times u dot? We will obtain it. Now you know that the three-dimensional velocity vector u, this is defined as uxi plus uyj plus uzk. And when you find the modulus u square, then what is this? This is equal to ux square plus ui square plus uz square. Okay, so u square is equal to ux square plus ui square plus uz square. Now our aim is to find the value of u times u dot. So let us differentiate this equation with respect to t. So this will be d dt u square equal to d dt this much, ux square plus ui square plus uz square. Okay, now when you will differentiate u square with respect to t, what will be the result? This will be 2u into du by dt, and this operator d dt will be operated on each term separately. Okay, so this will be 2ux dux by dt plus 2uy duy by dt plus 2uz duz by dt. Okay, now as you can see, 2 is a common factor as it is present in each term, so 2 will cancel out, and du by dt is written as u dot. So this is u times u dot. Again dux by dt, this is ux dot, so this is ux times ux dot. Similarly, this is uy times uy dot, and this is uz times uz dot. Okay, now as you know that the scalar product of any two vector, that is three-dimensional vector, this is equal to ax times bx plus ay times by plus az times bz. Okay, so at the place of a, here there is in fact at the place of ax there is ux, and at the place of bx there is ux dot, and similarly at the place of ay and by there is uy and uy dot, at the place of az and bz there is uz and uz dot. Since it is equal to a dot b, so this expression in RHS can be written as vector u dot vector. Okay, so in this equation which we have obtained for the first component of the acceleration 4 vector, we will substitute u dot vector instead of this u times u, and substituting that, what will be our result you can easily see. This will be a1 equal to 1 over 1 minus u square by c square to the power half times ux dot over 1 minus u square by c square to the power half plus ux times u dot vector and divided by c square times 1 minus u square by c square to the power 3 by 2. Okay. Now, when we will multiply by this factor 1 by 1 minus u square by c square to the power half to the terms inside this square bracket, our result will be a1 equal to, sorry, this is just a common defect of my iPad because it has become old and it needs some remedy. So see here, a1 will be equal to ux dot over 1 minus u square by c square plus ux times u vector u dot vector over c square times 1 minus u square by c square whole square. Okay. When you will multiply by this factor, this will be your result. So in this way, you can see we have obtained the first component of the acceleration 4 vector. In fact, in the similar manner, you can directly write the expression for the second and the third component of the acceleration 4 vector just by induction. You have only to change the subscript. Instead of a1, we will now write a2. Instead of x, then we will write y. So our expression will be a2 equal to uy dot over 1 minus u square by c square plus uy times vector u dot vector over this much. Okay. And when you will write a3, then instead of ux, you will have to write uz. So this a3 will be equal to uz dot over 1 minus u square by c square plus uz times vector u dot vector over c square times 1 minus u square by c square whole square. So the first three components of the acceleration 4 vector has been obtained. Now we will find what will be its fourth component. Let us see. The fourth component, which is denoted by the symbol A4, this will be defined as du4 by d tau. Okay. Again, this du4 by d tau will be written as du4 by dt times dt by d tau. But you have just learnt that this u4 is equal to what? u4 is equal to this much. You have just learnt. This is IC divided by root over 1 minus u square by c square. Okay. So this will be d dt this much. Okay. And you have just seen earlier that dt by d tau is equal to this much. That is 1 over root over 1 minus u square by c square. Okay. Now here IC is a constant factor. So we will simplify this RHS in this way. This will be IC over root over 1 minus u square by c square, and the operator d dt will be operated on what? This will be operated on 1 over root over 1 minus u square by c square. So if you will write this factor in numerator, then this will be 1 minus u square by c square to the power minus half. Okay. Now let us differentiate it. This factor has been written at is, you can see. Now 1 minus u square by c square to the power minus half is to be differentiated with respect to t. So this is just a function of function. First of all, this will be differentiated with respect to 1 minus u square by c square, and that will be minus half into 1 minus u square by c square to the power minus 3 by 2. And then 1 minus u square by c square, this will be differentiated with respect to t. Since 1 is a constant, its dc will be 0. Now, c square is also a constant factor, so in denominator this c square will remain at its, and we will now differentiate u square. This will be 2u times du by dt. But instead of du by dt, I have written here u dot, you can see. Okay. Now again you can see this 2 and this 2 will cancel out. Okay, and one of the c, this c and this c square, this will cancel out. Okay, and so finally we get, and this minus minus will become plus. So finally we get that this A4 is equal to I times u dot over c times 1 minus u square by c square whole square. Okay, why whole square? This will be when in the denominator power will be plus 3 by 2, and that power and this half power when we'll add it, that will be 2. Okay, so this A4 is now you have seen that this u times u dot is equal to vector u dot vector. So this expression is written as A4 equal to I times vector u dot vector divided by c into 1 minus u square by c square whole square. Okay, so in this way you can see we have easily obtained all the 4 components of a 4 acceleration vector. So now let us write the expression for this 4 acceleration vector a mu. You know, the first component a1 is equal to this much. I am not giving the reading, you can see you have just obtained. This is actually at the place of a2, you can see, and this is actually at the place of a3. Okay, and this is at the place of a4. Okay, now you know that this ux dot uy dot and uz dot, ux dot uy dot and uz dot, these are actually the components of acceleration vector in 3D space. Okay, so if you write the acceleration vector in 3D space by the symbol vector a, then a is defined as du vector by dt, that is u dot vector, and that will be equal to ux dot I plus ui dot j plus uz dot k. So combining all these 3 terms, that which I am just taking, when you will combine it, this, and this, then you will get the resultant acceleration vector a in 3D space and divided by 1 minus u square by c square. Okay, and again when you will combine these terms, see here, which I am just crossing, these 3 terms, one is for x, another is for y, and this is for z. Then uxi plus uij plus uzk, this is equal to vector u. So instead of this ux, uy and uz, I have written here vector u, you can see. And u dot is replaced by vector a. So this component is actually the three-dimensional acceleration vector a divided by 1 minus u square by c square plus u times u dot a divided by c square times 1 minus u square by c square's whole square. There is also whole square. This is actually the acceleration vector in 3D space. Okay, and the 4th component is this, you can see, this is I times u dot a divided by c times 1 minus u square by c square's whole square. Okay, and this, in this way you can express all the 4 components of this acceleration 4 vector. I think you have understand these concepts very clearly, because this was a very simple concept, and so definitely when you will watch the video you will enjoy it. Okay, now in the next lecture we will see only one example of the 4 vector, and that is very important 4 vector, which is called force 4 vector. Okay.